So in this video, we're going to be looking at our next topic. So we're still working in section 4, and topic 3 is radioactivity. And this is a really interesting topic and quite a controversial one sometimes. But we're going to have a look at radioactivity and see that it occurs in everyday life. And if it didn't occur, we would not be living on Earth. So our first subtopic is called stable and unstable nuclei. Okay, this is relatively short, and I just want to go through a few key issues. Now, first one, not all atoms have a stable nuclei. So in your general day-to-day lives, the things we see, the things we do, you're using a table right now, sitting on a chair, writing with a pen. All of those things have atoms in them, and they'll all have stable nuclei. Okay, but not all atoms have stable nuclei. And what that means is we have some atoms that decay and they can't actually stay at that. So, for example, say your table is made of carbon, it's always going to be carbon. It's never going to decay away. But there are some atoms that cannot stay in that state, and they will be there for a brief time, but eventually they'll decay away. So they don't have any stable nuclei. Okay. So we're going to have a look at a graph in a moment, but basically, when we talk about stable nuclei, if it's a low mass, so anything at the start of the periodic table, we basically have equal numbers of protons and neutrons. All right, so if I have a look at this graph here, now we've got neutrons on the y-axis, protons on the x-axis. And basically what happens is these are basically equal up to a point, and then they start to become different, all right? So these are not overlapping on this graph, but basically that's what's happening in real life. Our neutrons and our protons are going to be the same in our atoms until we get to a certain point, and then we start getting more neutrons. Okay, but that's our next point, all right? But firstly, we'll say low mass. They have equal numbers of protons and neutrons. And if we're talking about high mass, we have more neutrons than protons. Okay, so again, when we've got low mass, so low neutrons, low protons, we're basically the same for a stable nuclei. They're basically a 1-to-1 ratio. So as we know from helium, we've got 2 protons, 2 neutrons. And that trend's going to continue throughout. So lithium generally has 3 protons, 3 neutrons, and so on. But we get to a point where we need to have more neutrons. Now, the way I want you to think about this is I want you to think about neutrons as the nuclear glue. Okay? So they keep the nucleus stuck together. All right, so when we've got a small mass, we only need a little bit of glue to keep it together. So we just have, if we have 1 proton, we usually have 1 neutron, and that's enough glue to keep the nucleus together. And as we move forward, that's fine. But as we get to higher numbers, we need more glue to keep these together. Okay? And that's how I want you to think about this. I want you to think about neutrons as nuclear glue. Now, another thing we want to think of is our stable nuclei. You can see this graph here. It gets to this point and it goes off the chart. Now, that's no error. That's not, and it's not a random number. Stable nuclei, they occur up to 83 protons. Okay. Beyond that, there are no stable nuclei. Everything's going to decay. So up to 83 we have stable, and beyond there we don't have stable. Okay, and I just want you to remember that the neutrons are like nuclear glue. As we get more protons, we're going to need more glue. All right, but at the start, we basically need a 1-to-1 ratio. Okay, so that's the general form of the nucleus, the neutron to proton ratio, and we're going to have another look at this later, but we're going to jump to the next subtopic. So this next topic is types of decay of unstable nuclei. Okay, so we're only going to be looking at unstable nuclei here because obviously stable don't decay. The first point, and this is the whole concept of this section. So unstable nuclei decay by the emission of radiation. Okay, so the way they decay, when we say it's unstable and it decays, what it does is it emits some form of radiation. Okay, and we're going to have a look at 4 of those kinds. Now, there's 4 types of decay that we care about. Okay, there's many more, but the ones we're interested in, there's about 4 of them. Well, there's 4 of them. Now, the first one is called alpha decay. So alpha decay is the emission of a helium nucleus. Okay, so all of these are going to emit something. The first one is going to be a helium nucleus. Okay, so what a helium nucleus is helium, got a mass of 4, and it's got 2 neutrons. Okay, now we also call this an alpha particle. Okay, so we have used the term before, alpha particle, and what an alpha particle is just a helium nucleus. So this decay occurs when a nuclei emits an alpha particle. All right, the next kind is beta minus decay. Now, beta minus decay is when our nucleus emits an electron. Okay, so that's where the minus comes from. So we're going to emit an electron. Okay, so all of these decays emit something, and that's what I've put here. So that's an electron, and we can also write that as just an E minus. All right. Now the next one is going to be clear why we call this beta minus, not just beta, because we have the next kind of type of decay is beta plus decay. And what we emit there is something called a positron. Okay, now we haven't really used this term formally, but basically what a positron is it has exactly the same properties as an electron. Okay, so we're gonna give it an E, but like it suggests here, it's beta plus, and it's called a positron. It has positive charge. Okay, so it's exactly the same as an electron, but positive charge. So same size, same mass, same everything, except positive charge. And this is a type of particle. And I'm just going to make a little note here. This is not vital, but it's called antimatter. Okay, so you would have heard of antimatter before. Okay, and this is our first type. So it's exactly the same as an electron, except opposite charge. And finally, we have spontaneous fission. Okay, now what this is, I'll get my blue back, is when we have a nucleus, and the nucleus splits in 2. Okay, so you might have some large nucleus and it just splits into 2 smaller ones. So that's called spontaneous fission. Now what we're going to look at next is when each of these occurs. So firstly, we're going to have a look at when alpha particles occur. Okay, and we're going to have a look at a graph that is exactly what we looked at before. So it's exactly the same as this. So it's a graph of neutrons to protons. Okay, I've just sketched it up here. Okay, so we know that we have stable nuclei up until the number of protons equals 83. Okay, and beyond that we don't have any stable nuclei. So what we say is that beyond this point, it's supposed to be an arrow, beyond this point atoms are too large. Okay, it's a bit of an informal definition, but we say atoms are too large. Their atomic number Z is greater than 83. Okay, and what we get here, I'll just sneak it in here. This leads to alpha decay. Okay, so I'll just make that a little bit clearer. Alpha decay. So when we have greater than 83 neutrons, we get alpha decay. Okay, so the next area and the next emission we looked at was beta minus decay. Okay, now beta minus decay occurs in this area of the graph. So if we've got an atom that has too many neutrons, it lies here, it lies above that stable line. What we say is, so like I just said, we've got too many neutrons. Okay, so there's too many neutrons in the nucleus. So what happens is a neutron is converted to a proton. Okay, and that can happen. That's perfectly fine. But we need to conserve charge. So if we've created a proton, we've created a positive charge. So what this means is an electron is emitted. Okay, because we started with a neutron which has no charge. We created a proton, positive charge. We have to create a neutron to negate that positive charge. Okay, and that occurs above this stable line. And I might just indicate that here. This line here is all the stable nuclei. So the final area on this graph is down here below the line. Okay, I'm hoping that comes up. Yep, that's not too bad. Okay, so if we get a nuclei below this stable nuclei line, okay, so you can either think of that as not enough neutrons or too many protons. Okay, I'm going to write that down. If we have too many protons, okay, that looks fairly clear on my screen, so I hope you can read that. So we've got too many protons. A proton is converted to a neutron. Okay, because a proton is converted to a neutron, we have to conserve charge, and so we release a positron to conserve charge. Okay, so it's exactly the same as the electron, the theory. So we went neutron to proton to conserve charge. We have to go electron. Here we started with a positive charge, we went to neutral, so we have to emit a positive charge to maintain it. Okay, so those are the three regions of our graph and the corresponding decay that occurs in those regions.